Good afternoon. My name is Chris Finfrock. I'm a PhD student at Colorado School of Mines working with the Advanced Steel Processing and Products Research Center. Today I'm going to share a talk about some research work performed to elucidate the effect of strain rate on stability of austenite in quenched and partitioned microstructures. The motivation for this work is that automotive lightweighting has the potential to greatly reduce anthropogenic greenhouse gas emissions. In fact, improving fuel economy has been mandated by the USA with the CAFE standards. A great way to reduce body and white mass is to reduce gauge thickness of the steels used to construct the vehicle. However, to maintain an acceptable level of passenger safety, we need to maintain the energy absorption and anti-intrusion characteristics of the vehicle. The equations reported by Abuaziz, shown here, suggest that we must increase yield strength and ultimate tensile strength if we want to reduce thickness while maintaining energy absorption and anti-intrusion characteristics. A further challenge is that new steels must exhibit acceptable work hardening characteristics so that they're formable. Quenching and partitioning has emerged as a novel low-cost heat treatment that provides exceptional mechanical properties in lean alloy compositions. In this process, we either intercritically anneal or fully austenitize the steel. Subsequently, we quench the steel to a temperature between the martensite start and the martensite finish to create a microstructure containing a controlled volume fraction of martensite. Then, in a subsequent partitioning step, we allow the supersaturated carbon in the martensite to diffuse into the remaining austenite, thereby stabilizing the austenite at room temperature. In effect, Q&P creates a highly refined and complex microstructure containing martensite, metastable retained austenite, and perhaps intercritical ferrite. The primary benefit of retaining some austenite in a steel microstructure is that retaining austenite greatly enhances ductility and work hardening via the trip effect. The trip effect occurs due to the deformation-induced transformation of austenite to martensite. To provide you with a tangible example of a commercially available Q&P steel that takes advantage of trip, take these two steels, QP 1000 and QP 1200, as an example. Both steels contain fractions of martensite and retained austenite. In the case of the lower strength and higher ductility QP 1000, the microstructure also contains controlled volume fractions of intercritical ferrite. Two characteristics of tensile mechanical behavior should be pointed out. First, both steels have a very high yield stress due to the presence of tempered martensite. Second, both steels have high instantaneous strain hardening exponents at high true strains. This high work hardening is due to the deformation-induced martensite transformation. Of course, the utility of this relatively high strain hardening exponent is that the onset of necking is suppressed through the instability criterion. Furthermore, by tailoring the stability of austenite, perhaps we can improve the formability and toughness of these materials. For comparison, a more conventional steel would show a strain hardening exponent that simply decreases with respect to strain. So if we intend to rely on the trip effect to enhance the mechanical properties of our Q&P steels, then we should understand what factors control trip. In a comprehensive review, Demore showed that neither strength elongation product nor any other measure of tensile mechanical performance could be correlated to austenite volume fraction. Rather, Demore argued that other characteristics of the microstructure, such as the mechanical and chemical stability of austenite, were just as important for dictating properties. So based on an ongoing literature review, I've concluded that the main factors that control trip can be divided into microstructure characteristics and deformation processing factors. The first can be controlled at the steel mill, and rather the latter can be controlled during sheet forming or in a vehicle crash. For example, we can control alloy distribution in the microstructure at the mill by modifying the Q&P heat treatment parameters. Likewise, we can control strain rate during a stamping operation by adjusting the tool displacement rate. For my PhD work, I've elected to focus primarily on deformation processing factors, where I believe there's a large potential to clarify strengthening contribution of the trip effect. Today, I'll focus my talk on the convoluted roles of strain rate and adiabatic heating. Based on experimental data from this study and a review of previous research, I postulate that the strengthening contribution of trip is controlled by the competing effects of, first, a decreased chemical driving force for deformation-induced martensite transformation that is caused by deformation-induced heat accumulation at higher rates, second, an increasing number of martensite nucleation sites, and third, an increasing mechanical driving force due to strain partitioning from ferrite and martensite at low rates to austenite at high rates. Generally, the strain rate dependence of these factors gives rise to a trough-like behavior in terms of deformation-induced martensite transformation and ductility. I've represented this with an arbitrarily drawn curve here because the trip community has not fully evaluated the nature of this curve. The presence of the trough is well established in the literature, but I'd like to discuss some aspects in greater detail. So this table lists papers that have reported the effects of increasing strain rate on the deformation-induced martensite transformation, and each column represents a microstructure created with different alloying and thermal processing. Generally, austenite stability and austenite volume fraction increases from left to right, with the Q&P and trip steels containing around 10% austenite and the stainless steels containing about 100% austenite. For very high stabilities and volume fractions of austenite, i.e. stainless steel, medium manganese steels, the deformation-induced martensite transformation is categorically suppressed by increasing strain rate. This has really been attributed to adiabatic heat accumulation to above the MD temperature during deformation. This is not always the case for Q&P steels. In some cases, for example in Whitney Polling's work from the Steel Center, increasing strain rate did not drastically alter the extent of transformation. Interestingly, at very high rates, Zhou, Wang, and Enlow have reported that martensite transformation is in fact enhanced. Ultimately, the presence of trough-like behavior suggests that there is the potential to optimize microstructure design and deformation processes to tailor the martensite transformation and mechanical properties. Based on the review presented, my hypothesis for this work is that if we understand the sensitivity of the martensite transformation to forming temperature and strain rate, then we can optimize microstructure evolution during deformation and vehicle crashes. Likewise, by tailoring the microstructure, we can improve the mechanical response. In the approach section, moving from left to right, I'd like to briefly share some of the tools we have used to address this hypothesis. First, in order to measure mechanical properties of our Q&P steels, we used uniaxial tensile testing. Second, to evaluate strain state effects on trip, we intend to perform formability experiments using a forming press. This forming press is new at the Colorado School of Mines and is equipped with heated tooling and a stereo DIC system. We've also used some novel instrumentation to resolve surface strain, phase volume fraction, and temperature evolution in situ during deformation. The images I'm showing here are from infrared thermography experiments at CSM and Hopkinson bar experiments at the Advanced Photon Source at Argonne National Laboratory. Finally, after deformation, we also measure characteristics of the material ex situ using X-ray diffraction and scanning electron microscopy. In this talk, I will discuss a few of these experiments in greater detail. To evaluate the hypothesis, 2 Q&P steels were selected for the study. Both were zinc-coated and fully finished on an industrial mill. Because they were designed to have ultimate tensile strengths of 980 and 1180 megapascals, they are designated hereafter as QP980 and QP1180. Both steels contain similar alloy contents and slightly different contents of intercritical ferrite, martensite, and retained austenite. Using optical microscopy, we determined that QP980 contains about 20 volume percent ferrite. Meanwhile, QP1180 contains much less ferrite. By X-ray diffraction, we determined both steels contain about 10 volume percent austenite. Comparing the effect of phase volume fraction on strain rate sensitivity is of interest to me. After all, ferrite is highly strain rate sensitive. However, for brevity, I will mostly share results from our QP980 steel today. To provide a view of the Q&P microstructure, an SEM micrograph of QP980 is provided in the lower left. The microstructure appears consistent with other Q&P microstructures reported in the literature. Ferrite, retained austenite, and tempered martensite are evident in the microstructure, and generally, the austenite exists in both blocky and film morphologies. The microstructure appears to be very fine. To evaluate the susceptibility of the retained austenite to transform in the base microstructure, interrupted tensile tests were performed at a quasi-static rate. In the center of the slide, a plot of true stress versus true strain is reported both for a monotonically loaded specimen and a sample that was interrupted every 2% strain for X-ray diffraction analysis. Generally, the deformation behavior between the two loading conditions was similar. However, some small yield points were observed in the interrupted condition. We suspect that these yield points are due to a combination of Kelly-Hassan phenomena at low strains and strain aging in freshly tripped martensite at high strains. My colleague Melissa Thrun has performed more analysis on these yield points. From the XRD analysis, we learned that retained austenite content decreased as a function of strain, suggesting that the trip effect is active in QP980. The retained austenite content decreased from approximately 9 to 5% during uniform elongation. We expect that retained austenite content continued to decrease in the region of the neck, where it was subjected to exceedingly high effective strains and a change in the strain state. After determining that the trip effect was active during interrupted tests at a quasi-static rate, we were interested in measuring the tensile mechanical properties of QP980 over a range of strain rates from quasi-static to intermediate. Here, I'm showing true stress versus true strain curves of QP980 deformed continuously at various rates. Despite nearly identical roundhouse yielding behavior for specimens deformed at all strain rates, the specimens appeared to exhibit strain rate dependent ductility. As strain rates were increased from 10 to the negative 4 to 10 to the negative 1 per second, the uniform elongation repeatedly decreased from approximately 19 to 14%. Of course, this could have important implications for the formability of these steels at industrially relevant non-quasi-static rates. From the true stress versus true strain plots, differences in the work hardening rates of various samples are difficult to detect by eye. However, in accordance with the instability criterion, I would suspect that the lowest strain rate specimen generally had the highest work hardening rate at high strains, and thus was able to suppress the formation of a neck for the greatest amount of true strain. Indeed, based on true strain versus instantaneous strain hardening exponent curves for each test, strain hardening in QP980 appears to be sensitive to strain rate and the amount of tensile strain. The lowest rate specimens are shown in blue on the left. Here, instantaneous strain hardening exponent increased during the progression of the test until failure. However, as the strain rate increased, the hardening exponent increased from small to medium strains, then decreased in the final stages of deformation. Accordingly, the higher rate specimens exhibited lower ductility in accordance with the instability criterion. Although these true strain versus instantaneous strain hardening exponent plots are helpful, we are interested in analyzing hardening with a method that can distinguish between the various microstructure mechanisms that accommodate strain at different stages. Although I don't show it here, we are currently attempting to apply modified CJ analysis for this task. With this ongoing work, we have observed that the low-rate specimens exhibit 3 stages of strain hardening, while the high-rate stages exhibit 4. Soares and Skowronek have attributed stages 1, 2, and 3 to the onset of plastic deformation near the yield stress, slip of mobile dislocations in intercritical ferrite, and strain accommodation by the trip effect, respectively. Meanwhile, the 4th stage, exhibited only at high rates, has been attributed to the exhaustion of the trip effect and slip in ferrite or bainite, martensite, and the remaining retained austenite. The presence of stage 4 hardening in the high-rate specimens suggests that the deformation-induced martensite transformation was suppressed in the final stages of uniform straining, facilitating the rapid decrease in the instantaneous strain hardening exponent. So, what aspects of the higher rate test stabilized the austenite and facilitated a decrease in the work hardening rate? Stabilization of retained austenite by adiabatic heating has been frequently identified in the literature, so we were curious if we could measure and model heat accumulation in the Q&P steels. We were particularly interested in adiabatic heat accumulation in part because the samples were too warm to handle after removing them from the tensile frame. Here is an infrared video that shows adiabatic heat accumulation on the surface of a Q&P 1180 specimen. The video is being played back in real time. You can see that the test only took several seconds to occur. Likely, the heat that evolved from deformation did not have time to dissipate into the environment. Thermal camera video showed us that the temperature rose from room temperature to 60 degrees Celsius at the UTS, and then up to 160 degrees Celsius in the neck during fracture. Another observation is that the extensometer pins appear to act as heat sinks on the surface of the specimen. This would suggest that deformation processing factors, like tool contact during stamping, play an important role to dictate the extent of heat accumulation. Based on the thermal camera data, we were curious to know if we could model temperature rise under fully adiabatic conditions. The model is based on the assumption that 90% of the work associated with the tensile test is evolved as heat, and the exothermic transformation of austenite to martensite provided no significant contribution to sample temperature. Some recent works in the literature suggest that heating due to transformation may not be negligible, but for the simplicity of the model, it's been omitted here. Experimentally determined stress strain data was fed into the model to predict temperature rise. In the plot on the left, it appears that actual heating that occurred in tensile bars deformed at the 2 highest strain rates was very similar to the temperature rise predicted from the adiabatic heating model. Meanwhile, the two lower strain rate specimens exhibited only very small temperature rises. This suggests that the adiabatic threshold was reached around 10 to the negative 2 per second. For reference, for QP980, a test at this rate takes about 20 seconds to occur. Throughout the talk, I've claimed that the deformation-induced transformation of austenite to martensite is suppressed at high rates. Again, this probably occurs due to a combination of factors, including adiabatic heating, strain rate sensitivity, and perhaps a change in the number of shear band intersections. For a representative tensile specimen deformed at 10 to the negative 3 per second, the figure on the left depicts example scan locations and XRD spectra used to calculate retained austenite volume percent in both the grip section, exhibiting nominally zero strain, and in the uniformly elongated gauge section. This technique was performed on samples from every strain rate to resolve the effect of strain rate on martensite transformation. The relative amounts of deformation-induced martensite transformation as a function of applied strain rate are shown on the right. The greatest transformation of retained austenite occurred at the slowest strain rate, suggesting that a greater volume fraction of retained austenite was available to facilitate trip. Generally, higher strain rate specimens exhibited less deformation-induced martensite transformation. However, variability in local austenite content prior to deformation caused some variability between replicates, as is shown with the error bars. I'd like to note that this behavior is very consistent with the lower strain rate side of the ductility and martensite transformation trough that I mentioned at the beginning of the talk. So, since we quantifiably measured the extent of the ductility and transformation trough for low strain rates, it's logical to perform experiments that resolve trip response at very high strain rates as well. This is an example of a recent high-rate experiment that was performed at the Advanced Photon Source at Argonne National Lab in February of 2020. With synchrotron radiation, we were able to record high-rate radiography and diffraction videos for Q&P steels deformed at rates of 1,000 per second using a Kolsky bar. Additionally, we were also able to record load displacement data. The videos that I'm showing here are synchronized. On the left, radiographic imaging shows the elongation, necking, and fracture of a QP980 specimen at 200,000 frames per second. On the right, we see ferrite and austenite Debye rings at 200,000 frames per second. Generally, the austenite peaks appear to become fainter during the deformation event, suggesting that trip is contributing to strengthening even at very high rates. A lot of work needs to be done to quantitatively analyze these data. This is my goal for the winter. I'd like to make a few conclusions. First, I believe that understanding strain rate effects on trip is critical for the adoption and acceptance of trip-assisted advanced high-strength steels, and in fact other advanced structural materials that incorporate trip for strengthening. In this study, we observed that strain rate critically influenced ductility over a range of strain rates from quasi-static to intermediate. Future work will continue to evaluate strain rate effects while also exploring the roles of strain state, texture, and temperature in formability and finished formed part properties. And with that, I'll wrap up. Thank you very much for your time. Please feel welcome to reach out via email because I know that the online forum may hinder questions on the day of the conference event. As a closing, here's a video of a happy plain strain specimen being deformed in our new forming press. Thank you once again.